So we got introduced to the idea of induction. So basically it's a phenomena that we see when we have a coil, a conductor exposed to a varying magnetic field. The word varying, changing is very important over here. So under that we saw three law, two basically. Under that we have two subdivisions, so on and so forth. So overall three laws. So one of that is your Lenz's law. So we are trying to verify and explain Lenz's law. This has to do with positive and negative, right? It has to do with the direction stuff. So the most simplest form of explanation is that energy cannot be destroyed nor created. So based on this, we can explain this theorem or this observation. So the funda is quite simple actually. Whenever I move something, right? What if this end becomes south end? We know that we have, say we have changing magnetic field, and we know that this will induce current, and current itself will generate its own magnetic field. This is own, this is external. Now, if this magnetic field is south, what happens? There is a pull, right? There is a pull. If I push this with 10 Newton, if the push is 10 Newton and the pull is say 1 Newton, overall what will happen? It will keep accelerating. So for lesser force or lesser work, we have a lot more work. And what happens if I happen to connect this magnet in such a way that it goes around, I can do that. If this is possible, all I have to do is connect it in this way, make it go through a railing and come back. So what will happen? It'll keep moving around. It will never stop. Is that possible? All right. So energy wise, we get to understand that this has to be north. We have to do work for converting some form of energy to another form. We have to do work. How can we do work? Only if there is a north over here. When I'm moving it towards, there should be a north again pushing it. This can't be a pull. It has to be a push. Right? It has to be opposing basically. Opposing whatever is happening over there with it. So in this case, this has to be a north. Has to be a north. Or in this south. So there has to be a push when this is moving towards. That's your direction of acceleration. And there will be, the current has to be in a particular way. So if I use our right hand thumb rule, right? So we get to see that for us to have a north, again, that's supposed to be a right hand. Let me do this. This is better. So for this to be a north, the current has to be in, this is anti-clockwise. Yeah. It has to be so. Now the question is, what if I'm pulling it back? Still, will it be north? Let's think about it. Say we'll make this as north. I'm pulling it back. So north and north, what will happen? It will push. If this was north, it will push. And again, what will happen? If I'm trying to pull it away at 10 Newton, this will push and overall force will be 11 Newton per se. Example. Say it's 11 Newton. So again, all I can do is connect it to a railing, make it go round and round, and we have a never ending energy. That again is not possible. So it should be a work against something. So whenever you're trying to pull something away, what has happened? What happens generally? Like say Velcro. When you're trying to open it, what happens? There is a pull back. That's why you have to put that amount of force for this to work. And so this has to be what? This has to be a correct south end. Right? We are working against. This has to be a pull. Here it has to be a push. Because we are applying a pull away, pull away. This has to be pushed towards. Again, these are just words. So don't try to match the words. Try to understand. This has to be south, right? Trying to pull, it's against this action. So it's like tug of war. If someone is trying to pull in tug of war, what happens? If someone is trying to pull, you also pull, is it not? That's how tug of war works. If it is a contest wherein, you know, people are pushing, right? If we are trying to push, no, you take it, something like that. So for opposing the other person's force, what needs to be done? We also have to push. So when there is a pull, we'll pull. When there is a push, we'll push. The same thing the coil is doing. That's it. If it's not doing that, then all I can do is I can do a very smart thing, connect it in a way wherein we have endless energy, and all the world problems will be done. There's no more need of petrol. There is no more global warming and all of that. Does it make sense? Now let's look at the direction of current. Obviously, it has to be clockwise. So let me try to do it. Draw the diagram that is. It would be knuckle will be that side. Sorry, we are looking at the knuckle. Our hand is that side. Here the palm is this. Here the palm is other way around. We are looking at the knuckle. So this has to be north to the left, and so the south is to the right. So the current has to be clockwise, and we have this structure. Basically, we need to do work. Without work, there's no transfer of work. When we are taking the magnet near, that is against the repulsion, we need to do work, pulling. When we are taking the magnet away, against the attraction. So pull is to do with attraction. And push is to do with repulsion. This is the entire funda. So I have the actual, theoretical stuff that is needed for your exam. This is how you have to present the answer. Lenz's law states the direction of induced current in a circuit is such that it opposes the cause or the change which produces it. The word opposes is important. Experiment to illustrate this law. So this is a setup. Set up the experiment as shown in the figure. You have your galvanometer, you have your magnet, right? Bar magnet, that's your setup, simple one. Procedure. When the north pole is moving towards the coil, the current induced is observed to be anticlockwise. By applying the right hand rule, we see that the coil generates a north pole. So we are looking at the current and then deciding on if this phase is north or south. When the north pole is moving away from the coil, the current induced is observed to be clockwise. By applying the right hand rule, we see that the coil generates a south pole. Again, this is an experiment to observe Lenz's law, nothing else. I gave the entire explanation, but this is how experimentally we got to see is what we are trying to understand over here. That's the agenda of this particular video. So now explanation, case 1. When the magnet is moved towards the coil, there is an increase in magnetic flux. Here the word increase. To oppose this change, the coil generates a magnetic flux in the opposite direction, thereby reducing the overall flux. Conversely, that's the opposite way. When the magnet is moved away from the coil, the magnetic flux decreases. To oppose this reduction, the coil induces a current in the same direction as the original flux, thereby increasing it. Whenever there is a decrease, it increases it. Whenever there is an increase, it will try to reduce it. So basically, the net change has to be 0 is what he's trying to do. To conclude, this verifies Lenz's law as stated above. So note, this video has all the information, write what is asked in the exam. So again, I'm giving end to end whatever made sense to me, the flow. Whatever is asked in an exam, you guys write that. If they want you to state Lenz's law, just state that. If they want to make you guys, asking you guys to show with an experiment, then you guys can do this. If they want you to explain, then explain, so on and so forth. So each of this is a separate aspect of the same law. Be smart about what you have to present on your answer paper.